Stop saying the universe is getting bigger. It's not expanding outward at all. The truth is, space itself is generating new space. It's like the distance between you and your house is stretching on its own. What's really going on here? In the next hour, we'll refresh your understanding. Actually, the universe has no outside. Some might argue, since it's expanding, it must be getting bigger. The problem is the expansion. Isn't matter moving into some larger space, but space itself generating new space. So in the next few dozen minutes, we will trace this concept all the way from Hubble's redshift to the microwave background and TV static, from the early universe the size of a beach ball to Einstein's so-called biggest blunder, the cosmological constant. In the end, you might discover that what we call the outside is perhaps just an illusion we can never reach. To make this abstract concept of cosmic expansion easier to understand, let's start with a simple analogy. Imagine inflating a balloon in your living room. Air is blown in, the rubber stretches, the balloon occupies more space. It can get bigger because there's room around it to go. Your living room is its outside. Because of this, we naturally think of cosmic expansion as the same thing. Space seems to be expanding into some larger cosmic room. If it's getting bigger, it should have a boundary. It should have an edge. This idea seems reasonable, but it precisely fell into a cognitive trap. Physics tells us the universe doesn't work that way. When space expands, it's not pushing into some external void because there is no external container or empty space waiting to be filled. As the universe gets larger, it also generates its own space. A better analogy is, if you want to draw a circle larger than the paper, you don't draw a bigger piece of paper. You make the paper itself grow to accommodate the line. This sounds awkward because in our everyday experience, all expansion grows into somewhere. Plants grow into air, cities expand into countryside, ice spreads over water. Thus, we subconsciously understand the world in terms of inside and outside. But if you are both the paper and the drawing, the concept of outside loses meaning. So the question is no longer where the universe is expanding into, but how we know space itself is growing. The answer comes from the most distant starlight. Scientists realized this counterintuitive fact by observing distant galaxies. Edwin Hubble discovered that the farther away a galaxy is, the faster it recedes. At first glance, this seems to suggest we are at the center of a cosmic explosion, as if everything is flying outward from here. But the real oddity is the galaxies aren't fleeing through space. The space between them is being stretched. A reversed balloon analogy makes this clearer. Think of galaxies as dots on the balloon's surface. When the balloon inflates, the distance between dots increases, but the dots aren't crawling on the surface. The surface itself is expanding. Every dot sees the others moving away, and no single dot is the center. Replace this 2D surface with our 3D space, and you get the key conclusion. The universe is not expanding into some external place because there is no outside for it to enter. It is growing while generating its own stage. This conclusion not only boggles the mind, it also puzzled geniuses of the past. Even Einstein initially refused to accept it. But the thing is, this seemingly impossible expansion is happening right now at speeds you can hardly imagine. Next, we need to answer a hard question. How do we know this isn't just a pretty analogy? The clue lies in the experience of light being stretched. When a distant galaxy emits light towards us, its wavelength is fixed, whether blue, red, or infrared. It has its own fingerprint as this light travels through space that is continuously growing. The path beneath it gets stretched longer and longer. Imagine walking on a moving walkway that slowly extends. Your stride hasn't changed, but the path is secretly lengthened. By the time you reach the end, the actual distance covered far exceeds your step count. For light, the result isn't traveling farther, but its wavelength being stretched. So when blue light from afar reaches us, it becomes red light. The key point is, this isn't the Doppler effect from an ambulance speeding past, where speed changes the frequency. Instead, space itself is stretched during the journey, increasing the distance between each peak and trough. This is cosmological redshift. It directly proves the growth of space, independent of the motion of objects within it. To put it more intuitively, a mechanism that can stretch the ruler of your three-dimensional world is pulling the wavelength of ancient starlight to a completely new level. Here's a magnitude enough to reset your worldview. The light from the most distant observable galaxies has its wavelength stretched by nearly a factor of 40. Intense ultraviolet light gets pulled all the way to faint infrared. This means that during its billions of years journey, the overall scale of the universe also increased nearly 40 times. Because of this, the galaxy you see in the telescope is small and dim. But when the light left it, the universe was much smaller than today, and it was much closer to the future Milky Way's location. Clearly, space isn't just getting a little bigger. It's undergoing a continuous and grand stretch. More crucially, this stretching isn't happening in some distant corner, but everywhere. Right now, the space in this room is also trying to expand. The space between your eyes and the screen is also trying to increase the distance. You don't feel it because electromagnetic forces between atoms hold matter firmly together. The force of expansion is utterly negligible on this scale. Only in the vast voids between galaxies, where this atomic glue is absent, can expansion freely play out, carrying them farther and farther apart. It's like raisins being carried apart in rising dough. The raisins aren't actively moving through the dough itself is expanding. So when you ask where the universe is expanding into, it's like asking where the dough is going. Remember, you yourself are part of the dough. But since space is stretching everywhere, how far can we actually see? To put it bluntly, we live in an invisible cosmic prison cell, whose walls are built by time itself. Looking up at the starry sky at night, you might think the entire universe is spread out before you, but the truth will overturn that perception. What you can see is probably less than 4% of the real universe. The reason is simple and cruel. The speed of light is finite. The age of the universe is finite. The farther you look, the farther back in time you see. When you look at the sun, you see it as it was 8 minutes ago. Look at Alpha Centauri, you see it for years ago. Look at Andromeda, you see it to 0.5 million years ago. The universe is about 13.8 billion years old. This means the oldest light has traveled at most 13.8 billion years to reach you. Galaxies beyond this light travel time effectively don't exist from your perspective because their light is still on the way. But don't forget, during this time, space has been expanding. Those distant galaxies, when they emitted the light we receive today, were much closer to us. By the time this ancient light finally arrives, expansion has already carried them to over 46 billion light-years away, so our observable universe is a bubble with a radius of about 46 billion light-years. Outside this bubble, there are more galaxies and stars, and even, perhaps, another version of you reading this very text. You can't see them, not because they aren't there, but because light hasn't had time to arrive. Thus, the part outside the bubble falls into the unobservable universe. This isn't a wall or barrier blocking you. It's a limit set by physical laws. You can think of it as a thick fog, limiting your view to a certain distance in any direction. You know there's a world outside the fog, but you can't penetrate it. Furthermore, if the universe is nearly infinite in scale, your tiny observable bubble's proportion of the whole can almost be written as a beautiful zero. To understand where this wall of time truly lies, we need to look back at the oldest light. The oldest light in the universe today is rushing towards you at 600 million miles per hour. It's older than the birth of the solar system, older than the formation of the Milky Way. Its journey began when the universe was only 380,000 years old. Back then, the universe was a hot plasma sea, so hot that atoms couldn't even form. Any photon couldn't travel more than a few inches before being snatched by a charged particle. As the universe continued to expand and cool to a low enough temperature, protons and electrons combined for the first time into hydrogen atoms. The thick fog finally cleared. The universe suddenly became transparent. Light could travel freely. This is the epoch of recombination. The first photons to escape are what we observe today as the cosmic microwave background, CMB radiation. It is everywhere, filling every cubic inch of space. Even the little static snow on an old TV and changing channels has about 1% originating from this primordial light. More importantly, it marks the edge of everything we can see. You can never see beyond this horizon because the earlier universe was opaque, like the inside of the sun. Events before 380,000 years are forever hidden. To state it plainly, the cosmic microwave background is that earliest brick wall. It defines the observational limit. On the surface, this wall is still receding. With each passing second, light that has traveled 13.8 billion years plus one more second reaches us. Therefore, the radius of the observable universe minus 1 by 1 light second each second, which is about 300,000 kilometers of new space entering our view per day. We can see about 16 billion more miles of the universe, but then you realize another layer. Although the screen is getting bigger, those light sources are being carried away by expansion. For example, a galaxy that emitted a photon 13 billion years ago is likely now over 30 billion light-years away. We see it as it was, not where it is now. This sense of dislocation, like the film zooming in while the actors move back, is the daily reality of cosmological observation. Even so, the CMB tells us an extremely crucial fact. The early universe was smooth to near perfection, with temperature fluctuations of only a few parts in a million. And it was these tiny ripples that eventually seeded today's galaxies. Now, let's turn our gaze to what might lie outside our bubble. Based on our measurements of the CMB, the universe is approximately homogeneous on the largest scales. This means no matter where you place your starting point, the composition and proportions are roughly the same. It's like a bowl of cake batter stirred extremely evenly. Every scoop has the same composition. From this, we can infer if our patch of observable universe contains about 2 trillion galaxies, then, in another region of the same size outside our world, there are most likely also roughly 2 trillion galaxies, the regions beyond that are the same. This pattern would extend patch after patch, even more thrilling if space is nearly infinite in scale and maintains this uniformity. Then within any given volume, all possible arrangements of matter will repeat somewhere else. This sounds like metaphysics, but the conclusion is mathematical. Finite microscopic arrangements plus infinite volume makes repetition inevitable. Thus, the earlier metaphor of the paper and drawing being one connects with the observational evidence here. We don't need to find an outside to contain the universe. What really needs tracking is how this paper is being continuously stretched, and how, as its scale approaches infinity, it fills in all possibilities, since this paper, on an infinite scale, might fill all possibilities. The most striking conclusion follows. Repetition is unavoidable. So let's use a deck of cards as a basis. If you could shuffle the deck an infinite number of times, an identical ordering would eventually reappear. The universe operates similarly. Only the cards are replaced by atoms and their arrangements. Therefore, in extremely distant places, there must necessarily exist another you reading this very text. This is not a metaphor, but a literal deduction, because in those regions whose light can never reach us, quantum mechanics has arranged matter in every possible way, including the exact arrangement identical to your state at this very moment. So, somewhere a version of you stops reading at this moment. Somewhere you were never born, and somewhere else you live in a completely different version of Earth's history. Mathematics even gives a sense of scale. These copies are about 10,115 meters away. This number is so large that if written out in full, the length of the digit string alone would exceed the size of the entire observable universe. That if space is truly infinite, such a distance is still finite, so somewhere another you has just realized this fact. Farther away, yet another you realizes that the previous you has also just realized this fact. However, all of the above rests on one premise. The world outside is similar to our patch. What if it's not? Recent observations suggest our patch of the universe might be a bit sparse, like a cosmic void with below-average galaxy density. If true, then crossing the observable boundary might reveal more crowded space, more galaxies, more black holes, more intense activity, or, conversely, it could be an almost empty deep void. Bolder theories push the view back to the very first instant, a brief but incredibly violent period of cosmic inflation. might have torn the whole into many pockets with vastly different properties. Pocket universes, they might have different physical constants, different particle spectra, even follow completely unfamiliar physical laws, rendering our textbooks obsolete the moment they cross the boundary. And in our pocket, everything seems normal simply because we happen to live in a pocket with the right recipe. But there's a deeper point that needs addressing. What if the universe isn't infinite at all? An infinite, expanding universe brings a seemingly neat paradox. How do you make infinity bigger? Mathematics says you can't. Infinity plus any finite number is still infinity. Multiply it by 2. It's still infinity. You can't add anything to something that already contains everything. Yet observation clearly tells us space is stretching everywhere. To resolve this hook, the key is to remove the intuition that equates expansion with becoming more infinite. A more accurate statement is the asterisk scale factor asterisk is increasing. Imagine an infinitely large grid paper, each square 1 inch wide. Now stretch the entire grid so each square is 2 inches wide. The paper is still infinitely large, the squares are still countless, but the distance between any two points has doubled. This is the essence of cosmic expansion. It's not adding more infinity to infinity. It's increasing the unit scale of this fabric, making all distances grow proportionally. Thus, two galaxies now 100 million light-years apart were only 50 million light-years apart when the universe was half its current size, pushing the inference further. If the universe is infinite now, then at the moment of the Big Bang, it must also have been infinite. The Big Bang then ceases to be like fireworks exploding from a point outward. It's more like infinite space beginning to expand simultaneously at every location, filled with energy. In other words, the Big Bang happened asterisk everywhere asterisk in infinite space. It has no center, no boundary, no outside. Any location can claim to be the center, because from everywhere the view of expansion looks the same. This perspective, on one hand, explains why we see almost the same universe in all directions. It also explains why we find no edge or center. On the other hand, it throws up new questions. If the universe contains infinite matter and energy, why don't we get infinite density? The answer lies in the definition. Density is total amount divided by volume. Even if both numerator and denominator tend toward infinity, as long as they grow at the same rate, the ratio can remain finite. Thus, the universe can place infinite matter in infinite space, while maintaining a finite average density on the order of a few hydrogen atoms per cubic meter. From here, the paradox becomes personal. In a truly infinite universe, any event allowed by physical laws will occur an infinite number of times. Not just another you, but every version of every story, tragedy and triumph, beauty and cruelty. All will play out somewhere. If this is unsettling, consider the possibility of a finite universe, a universe with an end. Forces more tricky question. What's outside the boundary? Can space really have an edge? What happens if you try to cross this edge? These questions lead many scientists to prefer models where space is very large or approximately infinite. Even if it's conceptually hard to imagine, it at least concluded the question of what's outside the boundary Combined with the latest CMB measurements, we either face an infinite universe or one so large we can't detect any curvature. The most straightforward explanation is that space extends infinitely in all directions. Thus, the getting bigger we see now isn't like adding rooms to a house, adding blocks of space outward. It's more like loosening the entire, already infinite, fabric. So what is it that drives this continuous stretching of the fabric? Mechanically speaking, the universe is producing new space from the near-nothingness of the quantum vacuum at a rate that would make any factory on Earth jealous, roughly calculated every second. The volume of the observable universe increases by about 11, followed by 78 zeros cubic meters. This number is so large that even if you counted one per second, the time required would far exceed the age of the universe. Multiply that time by itself billions of times, and it's still not enough. But the quantum vacuum isn't nothing. It's a perpetually bubbling foam, where virtual particles constantly appear and annihilate in extremely short times. This is quantum fluctuation *. It gives every point in space and energy. What's truly counterintuitive is this vacuum energy manifests through gravity. Unlike the gravity of matter, which pulls things together, vacuum energy produces repulsion. It pushes space outward. More space means more vacuum energy. More vacuum energy means faster expansion. Faster expansion means more new space. Crank this feedback loop to the maximum, and you get a runaway explosion *, inflation *. In the earliest, extremely brief instant, this process ran wild. The expansion rate of space exceeded the speed at which light could travel through space. This isn't making anything * travel * faster than light. It's the treadmill accelerating. Light running on the treadmill can't outrun the treadmill itself. During that time, a region smaller than a proton could be stretched to nearly the size of a basketball. In an unimaginably short interval, it sounds like science fiction. But the ledger of quantum mechanics demands it happen, as long as you can repay within a sufficiently short time. You can borrow energy from the vacuum in the accounting phase. The universe borrowed a huge amount of energy from the vacuum to start producing space, then used the expansion itself to balance the books. It's like taking a loan to buy a money printer, then using the printed money to repay the loan. The problem is, this mechanism worked too well. It only needed to produce enough space to solve several cosmological puzzles, but it didn't shut down immediately. It overachieved, producing far more territory than needed. Thus, our entire observable universe is just a small patch on this giant inflating fabric. Imagine inflating a balloon to the size of Earth, and all we can currently see is a pinpoint-sized spot. What's even more intriguing is, although the early inflationary explosion stopped, expansion continues today, just at a different pace, driven by another actor, dark energy, constituting about 68% of the universe's total content. Its behavior is almost identical to vacuum energy. It uniformly fills space and provides repulsive gravity, causing accelerated expansion. As volume grows, new dark energy continuously appears to fill the new space. It sounds like it's creating energy out of nothing, which seems to violate energy conservation. The key to resolving this lies in gravity's ledger. Gravitational potential energy is negative as space stretches. The gravitational binding energy between matter decreases. This increasingly negative energy can offset the positive energy of the newly created dark energy. The result is that the universe constantly generates new space while keeping the total energy balance near zero. According to this script, expansion will continue for an extremely long time, far beyond human imagination. Each moment, new space is born, new dark energy appears, and the cosmic stretch continues to accelerate. The universe grows, not to occupy some external place, but because expansion itself is creating its own stage. But even with this grandeur, the origin of all this still needs evidence to substantiate it. Where should we look for it? The clue isn't in distant myths, but lies in a very plain place. When you switch channels on an old TV set, among the static snow, a small fraction comes directly from the universe's earliest light. The answer is in that snow. In 1964, at Bell Labs, Arnaud Penzias and Robert Wilson just wanted to get rid of an annoying hiss in their antenna. They changed directions, calibrated equipment, even cleaned bird droppings off the antenna. But the noise persisted. It turned out it wasn't a malfunction, but the echo of creation. They had accidentally detected the cosmic microwave background radiation, the afterglow of the Big Bang, because space continuously expanded. This ancient light was stretched and cooled along its journey, today only about 2.7 Kelvin above absolute zero. Because of this discovery earned them the Nobel Prize and provided the most direct evidence for cosmic expansion. More importantly, this background light doesn't just exist. It carries the fingerprint of expansion in its spectrum. Initially visible light at about 3,000 degrees Celsius as space stretched, first slid into infrared, then shifted to microwave, finally extending to radio waves simultaneously. The brightness across the whole sky is almost flat as a mirror, uniform to only fluctuations of a few parts in 100,000. This perfectly matched the prediction of inflation. If there hadn't been a period of extremely rapid stretching early on to smooth out irregularities, we should see huge temperature differences today. But we don't. So the question advanced a step. Where did those residual tiny fluctuations come from? The answer lies at the quantum level. Inflation stretch subatomic quantum fluctuations to cosmic scales. These faint energy ripples later became the seeds for galaxies and stars. In other words, you can read this text here. Because quantum uncertainty was amplified by the universe itself to macroscopic scales. Next, the evidence was mapped. Through the COB and Planck satellites, humans mapped these temperature fluctuations in great detail. The result, when checked against the angular scale distribution, it matched the theoretical curve of inflation almost point for point. Based on this ancient microwave light, we can not only see, but also measure the universe. Geometrically, space is flat within measurement precision. Compositionally, ordinary matter is only about 5% of the total. Dynamically, the expansion rate and the age of the universe can be deduced to a narrow range more intuitively. The data also gives us a shocking sense of proportion. The entire observable universe today was once compressed into a volume roughly the size of a beach ball. Here, compressed doesn't mean stuffing things into a box. Space itself was tightly squeezed. That beach ball wasn't a container holding the early universe. It was the universe at that time. There was no outside, no surroundings, only that compressed lump of space-time. Then it began expanding and cooling, leading to the starry sky we see now. So where did the energy to inflate this space-time come from? To find the answer, scientists turned their gaze to a more stable celestial phenomenon. In 1998, the teams used Pypeus supernovae as standard candles to measure how expansion should be slowing down under gravity. The idea was simple. Compare the actual brightness of these supernovae with their standard brightness combined with their redshift to calculate how far away they really were. But when plotted, the conclusion was completely reversed. Distant supernovae were dimmer than expected, meaning they were farther away than the standard model predicted. In other words, the space the light encountered on its journey was stretched more than we thought. So the universe wasn't being braked, it was accelerating. This discovery also won the Nobel Prize and brought us face to face with a new character, dark energy. It now constitutes about 68% of the universe's total mass energy, more than all ordinary matter combined, and more influential than dark matter in the grand scheme. Its weirdness lies in the fact that it doesn't clump or dilute. Matter becomes diluted as volume increases, but the density of dark energy remains roughly constant during expansion. Thus, the larger the universe, the stronger its overall influence. Early on, matter and radiation called the shots. Dark energy was just background noise as matter was stretched thinner and thinner. Dark energy's repulsive effect began to dominate, taking over about 5 billion years ago. Since then, the universe has entered the accelerated era, projecting this trend forward. More and more distant galaxies will recede from us at rates exceeding the speed at which light can catch up, eventually falling forever out of the observable range. But what exactly is this invisible pushing hand? The mainstream candidate is vacuum energy, i.e., the ground state fluctuation of quantum fields in seemingly empty space. According to naive estimates from quantum field theory, the vacuum should be packed with enormous energy, but compared to observations, it's off by a factor of 10,120. This is arguably the worst prediction in the history of physics. So either our understanding of the quantum world is missing a key piece, or nature has some mechanism that cancels out almost all the vacuum energy, leaving only the tiny bit needed to drive acceleration. Beyond this, some propose dark energy could be a field permeating the universe. Others simply suggest rewriting the law of gravity on cosmic scales. Whichever route, the conclusion points the same way. Our ignorance about it is comparable to ancient humans looking up at lightning, but it is indeed continuing to shape the fate of the universe. Speaking of the universe's fate, we need to pull the lens back to an earlier moment. Many ask, if expansion was faster than light, what happened? The answer doesn't violate the principle that no object can exceed light speed, because what was moving fast wasn't an object, but the scale of space itself. In the extremely brief instant after the Big Bang, The universe entered the so-called asterisk inflationary epoch asterisk. The distance between any two points doubled and redoubled in an unimaginably short time, so fast that light couldn't keep up. Intuitively thinking, two ants standing on a rapidly inflating balloon. No matter how they crawl, they only move farther apart in terms of magnitude. Inflation increased the universe's scale by least YT times, and all this happened in about 10 to 32 seconds. For comparison, light only travels 30 centimeters in 1 nanosecond. Driving this crazy stretch was a quantum field called the asterisk inflating asterisk. Unlike many fields with zero ground state energy, it was trapped in a high-energy false vacuum, like a pool of water held high, able to supply space with a continuous stream of energy for a short time. The terror of exponential growth lies in its early stage is quiet and unassuming, but later it suddenly makes a strong surge. It not only smoothed out early irregularities, making the sky look almost uniform, but also stretched the universe to near flatness and amplified tiny quantum fluctuations into the seeds for all future structure. Your galaxy, your star, even the atoms in your body can be traced back to random fluctuations at that moment. But then a more unsettling question arises. If inflation really happened back then, why could it only happen once? The kind of quantum field that drove the initial inflation most likely still lurks behind the scenes today. Given the right conditions, it could trigger a new round of exponential stretching. It could start a new inflationary bubble. Anytime, anywhere, the bubble would form there and expand outward at near light speed. Everything along the way would be rewritten inside the bubble. A completely new set of physical laws would operate. Our atoms would be dissociated. The laws we know would instantly become invalid. And most crucially, we would receive no warning. But for inflation theory, this isn't the most startling inference. The greater possibility is that our universe is just one bubble in an infinite froth of universes. At this moment, as you read these words, countless other universes might be born elsewhere. Each comes with its own natural constants, different particle families, even different physical syntax. This sounds like science fiction, but it's actually a logical extrapolation of inflation theory. If it happened once, quantum fluctuations will make it play out repeatedly on a grander stage. Thus, bubbly universes are blown out one after another, each inflating, then cooling, perhaps even nurturing its own galaxies and planets. Our universe is just one of them. In other bubbles, gravity might be stronger, stars would collapse into black holes as soon as they ignited. Gravity might be weaker, matter could never clump together. Some bubbles have no electromagnetic force. Chemical reactions simply can't occur. Others remain eternally inflating, never cooling enough to form atoms. The vast majority of bubbles are too barren to inhabit, but in a truly infinite froth of bubbles, even the most improbable combinations will appear in some corner. Thus, the anthropic principle gets a new explanation. The reason we find ourselves in a seemingly finely tuned universe isn't that the universe was tailor-made for us, but because only such a universe can give rise to observers. In other words, we can see it because it allows us to exist. Next, the question becomes not just physical, but get philosophical. If there really are infinitely many universes, then every possible experience is playing out somewhere. The choices you didn't make are made by another you in another bubble. The tragedies you avoided befall another version of you. The dreams you left unfulfilled blossom in another branch of reality. In this way, uniqueness is diluted to the point of near meaninglessness. The weight of choice is distributed across countless parallel scripts. More tricky is testability by definition. Other bubbles are outside our world. They send us no light, leave no gravitational traces. We can neither directly prove their existence nor measure their properties. Because of this, many scientists are reserved about the multiverse. If it's not verifiable, it can't be considered strictly scientific. On the other hand, the mathematical derivation of inflation strongly points towards eternal inflation and the picture of a bubble cascade. The same set of equations that successfully explains early cosmic inflation naturally leads to the conclusion of continuous inflation in a larger space, constantly forming new bubbles in line with this. The subtle statistical patterns in the CMB closely match inflation's predictions, this, while not directly proving the existence of other bubbles, gives us more confidence that he might be living within. The best evidence supporting the multiverse. Up to here you might still think you're just imagining bubbles in 3 dimensions, but the latest physics attempts remind us reality might be stranger. What if inflation is happening in directions we cannot perceive? String theory requires space to have 9 dimensions. Besides the familiar 3, there are 6 extremely curled up tiny dimensions hidden right here, right now, just too tight for even particles to detect. We are likely like an ant walking on a garden hose, only able to move forward and backward along the tube, thus mistakenly thinking the world has only 1 dimension. If these extra dimensions truly exist, they might be expanding along with our 3D space. In that case, the question, where is the universe expanding, has another answer. Our 3D space might be a brain stretching into a higher dimensional bulk. The accelerated expansion we observe might be the deformation of this brain, occurring in the larger dimensions. Bolder brain world models even propose that all particles and forces except gravity are confined to this 3D brain. Only gravity can leak into the extra dimensions, which also explains why it appears exceptionally weak. If there are other brains parallel to ours in the bulk, they might be just a step away yet feel as far as heaven and earth in directions you can't see, even occasionally colliding. Some models simply interpret our Big Bang as a collision event between brains. The cosmic microwave background might be the afterglow of that impact. According to this concept, on super long time scales, the brains might repeatedly meet, each time like pressing a reset button, initiating a new cycle of cosmic evolution in our 3D space. There are even stranger speculations. While our familiar 3D space seems static, the extra dimensions themselves might be expanding, or some dimensions are growing, others shrinking, so the overall volume might not change, but our 3D slice appears to be widening. For now, these are all hypotheses, because we can't directly touch the extra dimensions. The Large Hadron Collider, searching for signs of particles seemingly disappearing into hyperspace, but so far no conclusive evidence has been found. This might mean extra dimensions don't exist, or it could mean they are even more compact than we thought. Even so, the mathematics of string theory still suggests extra dimensions are likely an indispensable piece for describing reality. Stepping back, even without those hidden directions, the shape of 3D space itself can rewrite the meaning of where expansion is going. General relativity allows for three geometric types: flat, like an infinite plane; positive curvature, like a sphere; negative curvature, like a saddle. Observations indicate our universe is either flat or so close to flat it's immeasurably slight. However, flat doesn't necessarily mean infinite. A piece of paper is flat, but you can roll it into a cylinder or glue the edges to form a torus donut shape. Locally, it's still flat, but globally it can be closed and finite. If space is indeed self-closing in some way, then expansion is just increasing the size of this closed structure. It's not entering some external warehouse. It's growing into a larger version of itself. Pushing this line of thought about closed geometry further, it could even leave observable traces. In a torus-shaped universe, light could travel all the way around and return to its starting point. We might see multiple images of the same distant galaxy in different directions. In the CMB, there should be repeating patterns from light circling multiple times. Astronomers have tried to find markers of a closed space in the cosmic map, but haven't found substantial evidence. This could mean two things. Either the universe is much larger than our observable patch, or, at least on the scales we can currently probe, it doesn't have such a self-closing structure. In other words, the universe might really be shaped like a donut, but this donut is so large that light hasn't had time to go around it once. If we pull our perspective back one step from space, we see that space and time are actually one entity, space-time. The question of the 4D space-time shape thus becomes more complex. Expansion not only stretches space, it also changes the relationship between space and time. In the early universe, everything was extremely compressed, and the passage of time was completely different from today, and the concept of simultaneous loses its unified meaning over vast distances. As space is stretched, time is also stretched. Thus, a seemingly counterintuitive scene appears. Some very distant galaxies appear to recede at speeds exceeding light speed, but they aren't racing through space. Space itself is carrying them away, while simultaneously stretching the ticks of time for those galaxies themselves. They are almost stationary. It's just the rulers and clocks between us and them that are changing all the way. Relativity tells us that from any location in the universe, the view of expansion looks the same. Every observer will feel they are at the center, with everything else moving away. No one has a privileged reference frame. There is no true external reference. More importantly, this stretching isn't an abstract concept. It can be directly measured. For example, in a nearby galaxy, a supernova might take 3 weeks from brightening to fading, but if the same supernova explosion occurs in a galaxy receding faster and farther away, The process in our eyes would be stretched out like slow motion. The reason is simple. The light carrying the event's information is stretched during its journey. Not only is the wavelength stretched, but the time interval between light pulses is also lengthened. So what we see is a time-stretched version of the event. Using an intuitive number, light from galaxies at the observable edge has a redshift factor of about 10. This means their events appear to us 10 times slower than local processes. This also explains why the age of the universe is actually perspective dependent. From our viewpoint, it's about 13.8 billion years old. But if you stood on one of those receding galaxies looking back at us, our patch of space would appear much younger. In other words, the early universe was not only more compact in space, but also in time. Many evolutionary processes that take billions of years today might have happened in much shorter ticks back then. The first stars, first galaxies, first black holes were all born in that rhythm. Furthermore, expansion shatters our innate intuition about simultaneity. Two events you think are simultaneous might not be so for an observer extremely far away. There is no universal now in the universe, only the present moment of each respective local area. And as dark energy's influence grows stronger, this time-stretching effect will continue to amplify. Future observers looking into the distance will see even more extreme time dilation until those events appear almost frozen. This leads to the script for the universe's future. According to current understanding, expansion will make matter and energy increasingly dilute. Over extremely long times, the universe will head towards heat death. Temperature differences are erased. Processes capable of doing work are completely exhausted. The whole world is left with a near absolute zero, uniform void. A rough timeline looks like this in about 100 billion years. The last stars will exhaust their fuel. No new stars will be born. The universe enters the degenerate era, dominated by cold stellar remnants. Further out, around 1034 years from now, protons might decay. The building blocks of atoms and planets will disintegrate on their own. The universe will be left with the electrons, positrons, and photons floating in the ever-expanding void. Pushing the scale even further, around 10,100 years from now, black holes will become the only significant energy source. They will slowly evaporate via Hawking radiation. The lifespan of supermassive black holes could even reach the order of 10,100 years when the last black hole evaporates into faint radiation. The universe will reach its maximum entropy state. No temperature differences, no chemical reactions. Computation cannot continue. Life has nowhere to exist unless the nature of dark energy changes fundamentally. In the future, accelerated expansion will push the world towards this icy endpoint. In the nearer future, the impact is also not gentle. As space-time is stretched faster and faster, distant galaxies will fall out of our observable range. They won't be destroyed, they will recede so quickly that their light can never reach us here. Later, even the cosmic microwave background radiation will be stretched into undetectable wavelengths. Astronomers of that future time will see only a lonely local group of galaxies surrounded by boundless empty void on all sides, the key evidence for the Big Bang will have long vanished. In comparison, an ultimate Big Rip scenario only appears in more extreme scenarios. If the strength of dark energy continuously increases, acceleration would overwhelm all known forces, from gravity, electromagnetism, to the strong force holding atomic nuclei together. All would fail, the universe would be torn apart from within. But regardless of which ending, one thing is certain. So-called empty space is not empty at all. The vacuum is a quantum furnace dot on the smallest scales. It is boiling. Virtual particles appear instantaneously, only to annihilate just as fast, too quickly for us to catch, yet leaving real physical traces everywhere. Imagine using a microscope with resolution far higher than an atomic nucleus to observe nothingness. As you zoom into the Planck scale, about 10 to 35 meters, the originally smooth fabric of space-time would bubble and churn like a boiling soup. Geometric shapes fluctuate between moments of life. Virtual particles borrow energy from the vacuum, and the uncertainty principle dictates. The more they borrow, the faster they must repay. Electrons and positrons appear in pairs, annihilate in pairs. The entire process might last only 10 to 21 seconds. Virtual particles with greater mass have even shorter lifetimes. All virtual particles, led by quantum field theory, take turns on this seemingly empty vacuum stage, and it is this invisible quantum furnace that determines how cosmic expansion, step by step, stretches the fabric of space-time. They are not metaphysics. They are entities that can leave fingerprints in the laboratory. The most classic example is the Casimir effect. When two metal plates are placed extremely close together in a vacuum, only virtual photons with wavelengths shorter than the gap can fit between them. Long wavelength ones can't enter, while outside the plates, long wavelength virtual photons still exist. This asymmetry between the inside and outside creates a pressure pushing the metal plates together. This force can be directly measured. You are literally feeling the pressure of the quantum vacuum. But what really made quantum foam famous in cosmology is that it should contribute to the vacuum energy density. When physicists calculated it, the result was absurdly large. According to theory, the universe should be expanding at a rate far exceeding observed values. To compare, the theoretical value is 10,120 times larger than the actual measured strength of dark energy. This is one of the most embarrassing failures in theoretical physics history. Either our understanding of the quantum world is missing a crucial piece, or the universe has some mechanism that cancels out the vast majority of vacuum energy. If we can solve this cosmological constant problem, we might uncover the true nature of dark energy. Perhaps that tiny, uncancelled remainder is the dark energy driving accelerated expansion, or maybe the universe suppresses most of the quantum foam, only letting through an extremely small amount. Or perhaps our calculation method is fundamentally wrong. There are even bolder ideas. The vacuum might be filled with hidden fields or extra dimensions that leak out vacuum energy. Or even the concept of empty itself is just an illusion from our limited perspective. Loop quantum gravity suggests space is woven from a network of countless discrete loops String theory sees it as the result of string interactions in higher dimensions. Whichever side you take, the conclusion points in the same direction. Space is not a featureless background, but a structured medium. Expansion might be stretching this medium, not creating more space out of nothing. But even with our still very limited understanding of the vacuum, the future picture it presents remains shocking. If acceleration really gets stronger and stronger, what would happen? One extreme scenario is the Big Rip asterisk. About 22 billion years from now, dark energy could become strong enough to progressively dismantle all binding forces in nature. The universe wouldn't cool down slowly over trillions of years, but would rapidly collapse in a short time. A rough countdown looks like this. About 1 billion years before the Big Rip, galaxy clusters are torn apart. About 200 million years before the end, galaxies like the Milky Way are shredded. Stars are pulled from their gravitational embrace. 30 minutes from the end, planetary systems gravitationally collapse. Earth would be flung away from the sun. The moon would also escape Earth. In the final few minutes, molecular bonds are broken. Gases dissipate. Oceans boil. Not from heating, but because the distance between molecules is stretched beyond the reach of intermolecular forces. About 10 to 12 seconds before the end, atoms and nuclei disintegrate. The strong interaction has completely disarmed. At the final moment, even distance and time intervals, the metrics used to describe the world, might lose meaning, of course. All this depends on whether dark energy continues to strengthen. If it remains constant, the Big Rip won't happen. The universe will keep accelerating, but slowly heading towards heat death. Current data supports it being basically constant, just not with high enough precision. Future, more precise supernova observations will continue to probe whether it is truly changing. If strengthening is confirmed, a specific countdown could be calculated. In 1917, soon after Einstein finished general relativity, he ran into a problem. His equations naturally predicted a universe either expanding or contracting. They didn't support a static and changing universe, but the mainstream belief at the time insisted the universe was eternal and static. To fit this observational impression, he added an extra term to his equations, the cosmological constant, lambda. He interpreted it as a bit of energy intrinsic to the vacuum, like a gentle repulsive force, exactly counteracting gravity, keeping the universe stationary. This patch seemed reasonable and actually held for about a decade, until Hubble used the large telescope at Mount Wilson to measure the distances and velocities of distant galaxies one by one, finding they were generally receding, and the farther away, the faster the recession. The universe wasn't static, it was expanding. This was the original prediction of Einstein's equation, before he added the constant, so he promptly discarded the cosmological constant, calling it his biggest blunder. Ironically, decades later, the 1998 supernova observations brought the cosmological constant back, because we found expansion isn't constant, it's accelerating. To drive this acceleration, you need an energy density that uniformly fills space and produces repulsive gravity. Its effect is exactly the same as the cosmological constant. In other words, if dark energy is the cosmological constant, then Einstein's initial intuition was actually remarkably prescient. His reasoning was wrong, but his direction was right. Looking more closely, the numerical value of vacuum energy is very small, but not zero, about 10⁻10 joules per cubic centimeter. This number seems negligible, but once multiplied by the volume of the entire observable universe, it exceeds the total energy of all matter and radiation, directly dominating the late-time evolution of the universe. The problem is, when quantum field theory calculates vacuum energy, the result is 10,120 times larger than the observed value. This is the famous asterisk cosmological constant problem asterisk, or asterisk vacuum catastrophe asterisk. Either our understanding of the quantum world is missing a key piece, or nature has a mechanism that cancels out almost all vacuum energy, leaving only a tiny balance. Some also propose that dark energy isn't constant, but a field that slowly changes over time, using this dynamic dark energy to circumvent the catastrophe. For now, based on astronomical data, the simplest cosmological constant model remains the best-fitting explanation, switching the lens back to Hubble's night of observation. At that time, the scientific community was still debating whether spiral nebulae were part of the Milky Way or not. Hubble used Cepheid variable stars as a standard ruler, directly measuring the distances of these fuzzy objects, 2 millions of light years and beyond, clearly establishing them as independent galaxies. Then, he plotted these galaxies' distances against their spectral redshifts on a graph. The result immediately showed a pattern. The farther away a galaxy is, the faster it recedes. This is Hubble's law today. Initially, he thought galaxies were flying apart through space, like fragments of an explosion, but that would place Earth at the center, clearly violating the Copernican principle. The more accurate explanation is that space itself is stretching. Think of galaxies as small dots on a balloon surface. Once the balloon is inflated, every dot sees the others moving away, and the farther away, the faster they recede, with no single dot being the center. Hubble's law thus became the first hard evidence for cosmic expansion. Its proportionality constant is the Hubble constant, describing how fast the recession speed is per unit distance. Hubble's initial distance calibration confused the types of variable stars, so the first value was too high, leading to a calculated universe age of only 2 billion years, even younger than Earth. Later, the calibration was corrected, and the age returned to a reasonable range. But the linear relationship farther away, faster recession held firm. From nearby galaxies to the most distant visible ones, they all follow the same curve. This curve not only moved astronomy from the era of 2D sky chart plotting into the era of measuring the universe in 3D, but also pushed a key question to the forefront. Will expansion continue forever? The answer depends on how much stuff is in the universe. Physically, there is a critical density line that determines whether the universe will expand forever or eventually turn around and collapse. Intuitively, expansion carries everything outward. Gravity pulls everything back. It's a contest of the amount of matter per unit volume. Exceed the critical value, gravity ultimately wins. Expansion slows, stops, reverses, heading for the big crunch, fall below the critical value. Expansion forever has the upper hand. The world gets diluted to near nothingness, marching towards heat death exactly equal to the critical value. The expansion speed approaches zero more and more, but never quite reaches it. Like throwing a ball with just the right speed, it will keep flying towards infinity, its speed slowly approaching zero. What's even more mind-numbing is this cosmic knife's edge has a density that looks almost like vacuum, equivalent to only about 5 hydrogen atoms per cubic meter, and yet it is this very value that determines the ultimate fate of all galaxies, stars, planets, and even us. For decades, measuring the true density of the universe has been seen as the holy grail of cosmology. It sounds simple: add up the mass of all matter and divide by the volume. But in practice, it's a mess, because most of the universe's content is completely invisible. Galaxy rotation curves gave away the secret long ago. Stars in the outer regions orbit too fast to keep them from flying off. The required gravitational mass is about 5 times that of visible stars. Thus, this invisible mass was given a name: dark matter. It doesn't emit, absorb, or reflect light. It only tugs on the visible world through gravity. We can only identify its presence indirectly by its effects on stars, gas, and galaxy clusters, including dark matter. The total density of the universe is only about 30% of the critical density. By this accounting, the universe would expand forever, eventually approaching heat death. But the arrival of dark energy rewrote the entire conclusion. Dark energy not only raises the total energy density, more crucially, it carries negative pressure in Einstein's equations. Such a component pushes space-time to accelerate its expansion. In other words, no matter how much ordinary matter there is, as long as dark energy is present, expansion will run faster and faster. Combining current observations, our universe is composed of roughly 27% dark matter, 68% dark energy, and 5% ordinary matter. Considering the negative pressure effect of dark energy, this recipe places the universe almost exactly near the critical density, as if finding a subtle balance between different geometric fates. This raises the flatness problem. Why is the density so close to the critical value? In most evolutionary models, the density should have quickly deviated from critical, either becoming too large leading to collapse, or too small leading to dispersal. To maintain just right, the initial conditions had to be precise to an unimaginable number of decimal places. Cosmic inflation offered a way out. During that period of exponential stretching, any initial curvature would be flattened out. By the end of inflation, the universe naturally approached critical density. But then the coincidence problem pops up. Why do we happen to live in a brief window where matter and dark energy are roughly comparable? Perhaps this is just an observer selection effect, only in an era where structures can form but haven't been diluted away completely. Can observers like us have the chance to look up at the sky and ask questions, pulling the view wider? The assumption of a single universe might not hold up. In the picture of eternal inflation, our observable universe is just a small patch of a larger inflating region. Quantum fluctuations would occasionally trigger new bubbles elsewhere. Universes inflate and cool individually, growing galaxies and planets. Some bubbles have stronger dark energy, expanding faster. Some have denser matter, evolving slower. Others have already undergone a big crunch or heading towards a big rip, bringing in the many worlds interpretation of quantum mechanics. And almost every microscopic branching derives a parallel version of history. Thus, the number of parallel universes has no upper limit. New branches are born every moment. In some branches, you experience heat, death, and others, you witness the big crunch. In many more branches, you continue living against the backdrop of accelerated expansion. Evidence is hard to find because these universes are causally disconnected from each other. Scientists have also tried to find fingerprints of bubble collisions in the CMB, but so far, no definitive conclusions. Even so, the multiverse idea has changed how we talk about expansion. For our patch of space, expansion is the overall growth. For the larger structure, it might just be one layer of a more complex performance. Returning to information and meaning, the problem becomes more personal. Every thought in your mind, every memory, is essentially an arrangement of matter and energy, and the expansion of the universe is slowly diluting these arrangements. This seems like it's destroying information, but physics says information cannot be truly destroyed. The asterisk holographic principle asterisk offers a perspective. All the information within a volume can be encoded on the boundary surrounding it. As the universe grows, the surface area of the boundary also increases, so the number of storage bits increases with it. Complexity still has room to expand. Quantum entanglement also stirs the pot. It allows particles separated by vast distances to maintain correlations, seeming to remind us that information is more about relationships than absolute position. The problem is, causal connections will be severed by accelerated expansion. Regions that could previously communicate will eventually move apart faster than light. Information gets locked in isolated cosmic bubbles, unable to interact macroscopically. The history of the universe is still imprinted in the large-scale structure and CMB patterns microscopically. Local information will be diluted to the point of irrecoverability, finally pushing the lens to the ultimate future. As dark energy continues to stretch space-time further apart, the CMB will be redshifted beyond detection. Distant galaxies will drop out of the edge of our world one by one. Future civilizations looking up at the sky might see only a few nearby galaxies. They wouldn't be able to measure expansion or see the afterglow of the Big Bang. They would reach a seemingly simple but completely wrong conclusion. The universe is static and eternal. Fast forward to about 150 billion years from now. Dark energy will have pushed the vast majority of galaxies beyond our world. Their light is stretched to wavelengths longer than the observable universe, resulting in their complete disappearance from observation. In the eyes of that era, only our local group remains visible. Meanwhile, the Milky Way and Andromeda, along with their satellite galaxies, will merge into one isolated, giant elliptical galaxy, quietly floating in the empty void ... for them. This clump of starlight is the entire universe. Simultaneously, the CMB will also exit the stage because space continues to stretch. The wavelength of this primordial radiation will be stretched longer than the observable universe itself, making it undetectable by any instrument. Thus, all evidence pointing to a beginning for the universe will be lost. Even the mysterious redshift-distance relationship of expansion can't be measured. Without seeing distant galaxies, Hubble's law cannot be discovered, and there's no direct proof that space is stretching ... Therefore, the universe they observe will appear completely static. Based on this perspective, future scientists would likely develop another cosmology, concluding that the single giant galaxy has existed since forever in an infinite, static, unchanging void. They might find it hard to imagine that the universe was once filled with billions of galaxies, moving apart in an expanding cosmos. In other words, they will live in a universe deprived of its own history. Furthermore, this loss of perspective will deepen over time. Future observers will also lose key clues about early evolution. The nuclear reactions that forged the first elements ended billions of years ago. Their traces only preserved in the chemical composition of the oldest stars, and becoming increasingly difficult to decipher. The result is an epistemological crisis. Intelligence and technology might still be advanced, but the universe offers almost no hints about its own nature. The methods might be the same, but with too little usable evidence. Conclusions will be skewed. This forces us to reflect. Could our current cosmological knowledge also be limited by our era? Have we already missed crucial information that only early observers could see? Information now erased by expansion? Perhaps civilizations born right after the Big Bang witnessed scenes we can never see. The same analogy extends to the ultimate future endpoint as space continues to expand. Processes supporting life will eventually become unsustainable because gas becomes too thin for gravity to pull it together into clouds. Star formation will cease completely. Existing stars will exhaust their fuel and gradually fade. Black holes will slowly evaporate via Hawking radiation. Ultimately, the vast void will contain only sparse elementary particles. The universe will approach perfect heat death if observers still exist then. The world they face will be even more deceptive. No stars, no galaxies, no structure. Just sparse particles floating in infinite emptiness. They would naturally assume the universe was always this monotonous, unable to imagine its former abundance. This progression from richness to emptiness pushes the question, where is the universe expanding, to its extreme. This question presupposes a seemingly reasonable but unnecessary premise. Expansion must have a purpose, an end point, a need to go fill some external space. The fact is more direct. Expansion is the reason. It provides a dynamic stage on which a brief and complex structure can appear. Galaxies, planets, even life only take the stage because there is this stage that can grow. Without expansion, the universe would either collapse immediately or remain forever in a monotonous state. But this brings us back to the starting point. In a universe that can create space, generate time, and simultaneously be its own stage, what does it mean to ask where is it expanding to? When you ask where the universe is expanding into, you are implicitly assuming a pre-existing outside, as if a balloon needs air, a city needs countryside. But the universe is not a balloon. The universe is space. When space expands, it is not entering some external place. It is, while expanding, creating the outside. This concept, therefore, precludes a stage independent of the universe, because the meaning of external is defined by the universe itself. This is not a linguistic trap, nor a failure of imagination, but the structure of reality. Thus, before expansion, inside and outside had no meaning. Expansion, while creating more space, also generates the rules that make spatial relationships possible. The universe is not expanding to some place. It is accomplishing expansion by becoming more universe, not by invading a so-called non-universe. Following this realization, our understanding of expansion also moves from a mechanical process to a deeper path. Expansion is like a reality bootstrapping itself, pulling itself out of nothingness, from simplicity to complexity. Every cubic inch of newborn space opens new possibilities for matter, energy, structure, and complexity. The universe isn't getting bigger or some predetermined endpoint. It is moving in the direction of being able to accommodate infinite potential. We are not passengers on a spaceship being carried somewhere. We ourselves are part of this self-creating process. Our consciousness, questions, and curiosity are the universe's way of knowing itself. The expansion we see is not separate from us, because we are part of the expansion. We are complex patterns self-organized from space, time, matter, and energy, and able to question our own meaning. From this perspective, the apparent paradox is resolved, and simultaneously a deeper mystery emerges. Since the universe can create space and time, is both stage and audience, then existence might be stranger than any science fiction. Perhaps we live in a self-creating, self-sustaining process with no beginning, no end, no inside, no outside. The universe is expanding into itself, making room for infinite possibilities, and also making room for beings like us. Looking back on this journey of questioning, the problem has taken us through inflation and arc energy, the multiverse and quantum foam, the beginning and end of time. And the most precious answer is actually right before our eyes. The universe is increasing possibilities. We are the ones articulating it. So when we finally arrive here, we find ourselves facing never just a cold cosmic model. It is both the expanding void and the entire stage upon which we are born. Think and doubt, just like the initial question. If the universe truly has rules, are they the product of order or the accident of chaos? Perhaps we won't get the answer for now, but that's not important, because the process of seeking is itself the meaning of human existence, and in the endlessness of time, we have only just turned the first page. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.